let's talk about chapter 1, about science. Can you guys all see this? Go away. Okay, cool. So let's talk about the evidence that the Earth is round. So, unfortunately, while a lot of the stuff in this textbook is going to be like Western focused, which means that we kind of like we're going to focus mostly on the Greek and Roman scientists, and then jumping ahead to the Renaissance scientists and then early modern scientists. I want to emphasize this is only part of the story. There's of course, a long history of Indian, Chinese, Islamic, Mesoamerican scholarship on a lot of stuff, and that's only starting it. Of course, there's like other people who've done lots of other important calculations to science and mathematics. I will be I will be first to admit that it was only relatively recently that inoculation, the precursors to modern vaccines, were actually technology developed by native Africans that were brought over by the African slave trade. It was actually right around the time of the Salem witch trials when Cotton Mather, being a little unpopular with all those witch trials, decided like, oh, this pandemic that we're having, we got to stop this. And so he brought inoculations from what was the guy's name? I'm kind of embarrassed I forgot his name already. But like the African medicine guy, African doctor, basically. So kind of interesting little history about that. That's kind of the first time vaccine or inoculations in America started, was as a way to stem bad publicity from the witch trials. Anyway, but yeah, this is an evolving area of research that we're kind of like learning about what people knew when. So this story in 20 years is going to look different than it does today. Hopefully, at least. I will try and incorporate as much as I can from other sources, but this textbook does have a certain focus, and I want to broaden it a little bit. That, just a smidge, as much as I can. It's a big project to do can't just be me, so I hopefully will humbly suggest you reach out and look more elsewhere besides this textbook. It's a good starting place, but should not be the ending point. Anyway. So, evidence that the Earth is round before modern measurements. So, we've pretty much always known that the Earth is round. First thing you can see it is like look at an eclipse, lunar eclipse. You can see that the shadow that the Earth casts is round. So actually, modern flat Earth is actually an invention of the internet age, not an ancient tradition. But it's interesting what happens. I'm actually gonna one of the assignments is going to talk about the modern anti-vax movement, which is actually not contiguous with the historical anti-vax movement from way back when they first invented smallpox. And that'll be one of the choices you can do to basically talk about how science is applied, the ball got rolling on anti-vax. I'm going to do some will be more philosophically minded, some of will be more scientifically focused. But all of them are going to be talking about whenever you have people, there's always going to be politics and there's always going to be room for mistakes. So hopefully we can all be cognizant of our own human biases. All right. So back to the but let's go ahead and talk about how science can go right, at least this part at least. So an eclipse is when light from one object completely or partially blocks light from another. It only works if the apparent sizes are the same. By chance, the sun and the moon are the same size in the sky, about half a degree in our vision. Where it's from horizon to horizon, that's 180 degrees, and so that they measure the sky in terms of degrees. So that's the size of the Earth and the moon. Don't stare at the sun to make sure that. You can do the moon, but not the sun. Don't do that on the sun. It's kind of hard to do. There's some clever tricks, but I'll kind of show you what you can do to actually look at the sun without looking at it. So another reason we know that the Earth is round is that the stars appear at different locations at different latitudes, or they might not appear at all. If you're in the southern hemisphere, you will cannot see Polaris. There's also a southern pole star, which is not as bright, called something octans. Can't remember off the top of my head. I just taught this course this last winter, and I forgot already. But there's a southern pole star too. It's just not as bright. Okay, so here is how Eratosthenes measured the size of the Earth. Of course, there are multiple different ways, and multiple different people, men and women, over the ages have measured the size of the Earth. We're going to talk about how Eratosthenes did it. Okay, any questions so far? So, when light leaves the sun, it travels outward in all directions. However, since the Earth is very far away from the sun, right here, the sun's rays that reach the Earth are roughly parallel to each other. Because, again, we're really far away, and we're only a small little fraction of the total sphere that would enclose the sun at the Earth's distance right here. So these rays are roughly parallel. Like the green ones here. Here's triangles getting bigger and bigger and bigger until it's way over to the sun here. And it's basically, these are parallel to each other. Not exactly, but pretty close from the poles here. All right. Raise your hand if you're more timeless. I'll be posting these slides as well for you guys to look over.
Thank you.
I'm sure that was wait, hold on. Do I have to make sure I've written this all down? I recommend you write some of the stuff down because it helps stick in your brain, but I'm not going to make sure, I want you to also pay attention to what I'm saying too. All right. Let's go on to the next one. So, Eratosthenes estimated the size of the Earth, 250 stadia. Here's how he did it. So, since the Earth is much further from the sun, these rays are all parallel. He basically had, on the same day, he heard of stories in Syene, in Egypt, Lower Egypt down here. Sorry, Upper Egypt, sorry. I always forget, since they're talking about how far the river is, it's reversed. It's Upper Egypt. Lower Egypt would be Alexandria, where the river ends, because it's going downhill, lower, even though it's north. And versus one in Alexandria, which is further north, has a shadow. So, you can basically estimate the size of the Earth. This angle theta right here is about 7.1 degrees.
I have a question.
Yes, go ahead, Kareem.
So, what is this stadium measurement?
Oh, this is another thing about how humans have always been the way they are. So, if you hence stadium, yes, it's not, but they aren't football stadiums. These are chariot stadiums. So, funny little story about that I like to tell about how humans have always been this way, and we've basically been the same level of intelligence and foibles. How many people know the Emperor Justinian of Eastern Roman Empire? Okay, so in the early Middle Ages, there was an emperor of Eastern Rome, sometimes known as the Byzantine Empire. They didn't call them that; they called themselves Eastern Romans. That he was gonna reconquer Italy and have that, but he was also a super big fan of chariot racing. I think in particular he was a Greens fan. There's the Greens and the Blues. And there was the equivalent of a soccer riot just for chariots that he had to flee the city from, that burnt a big part of Constantinople, modern day Istanbul, down to the ground. So we've always been this way. People have been super passionate about sports, even back in the early Middle Ages, even sooner than that. So we've always been this way. So yes, it's a chariot stadiums, and exactly what a stadia is a bit of a debate. We think we, depending on what you call a stadia, Jakeem, it could be really accurate, or it could be a little off. So there's a bit of scholarship about that, about what a stadia actually is. But it is referring to the size of a chariot stadium.
Okay, thank you.
Yeah, no, good question. Yeah. So the stadia refers to the size of a chariot stadium. Yeah. So we think that he got within a couple of percent. Oh, yes, Victoria.
I just wanted to see, since you said there is a bit of a debate on how big a stadia is.
Mm-hmm.
Just a quick Google search. It does say about 185 meters.
Mm-hmm.
Does that sound like about right? I guess.
No, yeah, that is one of the estimates they have. Yeah, but there is the book says it is this value in the book, but there is a bit of debate in there about exactly what it was. But yeah, it's it gives you a really good estimate. Were you about to say something else, Victoria? Okay. Anything it is, a really good accurate measurement. That we've been getting good accurate measurements of the size of the Earth, even back in. I just want to give you a timeline on this. This was in 235 BC. So this is we've known the Earth is round. Actually, the size of the Earth for that. The main reason why Columbus, now that we're reevaluating Columbus for a variety of reasons, but the main reason why he was laughed out of most of the courts in Europe was not that he thought the Earth was round, everyone else didn't. It's that he thought the Earth was either smaller or pear-shaped, so you could cut across the Atlantic figure because it's pear-shaped. Anyway, but the King and Queen of Spain were desperate, and so they sent him out sure, just take these ships, go away. Sure, give it a shot. And he almost died. And then he committed genocide. But I'm not going to get into that right now. But yeah, we've known the Earth is the size of the Earth for thousands of years. We just didn't know what was on most of it. Or at least Europeans, I should say. Everyone kind of knew what was going on around their own local area, of course. So.
And size is like circumference or?
Mm-hmm. Yes.
Okay.
Mm-hmm. Hold on, let me double check. I believe the 2500 stadia is circumference. Yes, this is circumference. The circumference of the Earth. Circumference of the Earth. What you do to have that is that you basically say, what's the fraction of the arc length of the whole circle? So if you have a circle here, let's do a circle. And let's do here and here. So if we have an arc length here, so if this is 7 degrees right here, the fraction of the total circumference is 7 over 360 degrees. So the fraction of the total circumference is 7.1 degrees over 360 degrees. Okay. And that turns out to be about 2%, or more accurately, equal to 1.97 2 repeating percent. Repeating all forever. And if you multiply that, you basically divide this by 440 stadia, you get this number here for the circumference. Then you divide that by 2 pi and you got the radius. Or divide by pi and get the diameter. Yeah, and I think as Victoria said, the book says, let me just double check. That it's about 800 kilometers. That's like, well, sorry. That 440 stadia was about 500 kilometers. 800 kilometers, I mean. It's about like how accurate you can measure a distance. Because actually, if you don't, how can you measure a distance this accurately over long distance? You kind of just had someone pacing it out. How do you make sure they're going in a straight line? A whole bunch of things that they had to make sure they did right. Because the Earth doesn't tell you whether you're going due north or south or not unless you got compasses. And I think they were in China and India. I don't think they quite made it there yet with compasses. Even then, there's some when we talk about magnetism, we'll talk about how that can be also good guide, but maybe not get you exactly what you want. But anyway, this is like a really interesting way to actually calculate the size of the Earth. Any questions on how you calculate the size of the Earth? So you guys, in principle, could do it. This is what's so awesome, is that you guys could do it. A lot of science is like, it's too big for you guys to do. If you had 2 locations on the Earth, and you know the distance between them, and you measured the shadow on one and the shadow on the other, you could figure out the size of the Earth too. Maybe with big error bars, but it's still something you could do. Okay. Let's talk about the size of the moon next. What's going on here? So another Greek scientist, like I said, we're focusing on the Greeks and for this textbook, is Eratosthenes. Oh, sorry, that's right, Aristarchus. Sorry, misspoke there. So Aristarchus hold on one sec, sorry. I just want to rearrange some stuff. There we go. There we go. Okay. Sorry, I have to rearrange the multiple windows I have.
Question.
Yes, go ahead.
Is the word star being in his name something that gave way to astronomy, or is that just happenstance? His name,
Sorry.
Aristarchus, star being in the root, is that something that's happenstance, or is that something that gave us?
Huh. I don't know.
Okay.
I don't know whether it was like a title since he was like really astronomy focused. I don't know. That's actually a good question, Adi. I'll have to look into that. Or just like, being named after the stars would be a, kind of typical name you'd want to have. Yeah, I'll have to look into that. That's a good point. I don't know. I actually don't know very much about Aristarchus. Besides what he did. I'll have to look into it. Good question. So let me go ahead and grab this from the textbook about how you can measure the size of the moon. If I had to guess, it probably was his name, and then he, it's like, sometimes names kind of, people like grow into their names sometimes. That's what I get the feeling it probably was, but who knows? Maybe it was a title. So if we know the diameter of the Earth, and we know, yes, there is the, you have access to the textbook. In fact, we're going to take a break in 4 minutes, and I'll show you what it is. The Hewitt's physics, conceptual physics. That'll be where I'm going to draw the problems from and what you should be reading. And like I said, with the biases aside, that it's very, Eurocentric based. Leaving that aside, it still is a very good conceptual physics. Just, you should be added a little bit, and you should be aware of those lenses that are always there. Yeah, so, but yes, there is a textbook. That textbook is good, just it has some biases, like we all do. All right. So, Aristarchus calculated the diameter of the moon. Oh, yes, Samuel, you have a question? Okay, no. From the solar and lunar eclipses. Okay, so I already talked about what the lunar eclipse is. It's when the shadow of the Earth blocks. I don't know. No, I don't know. Yeah, I really don't. As long as you have access to the textbook, it doesn't really matter to me where you get it from. Whether it's used or one of those sites that I have never visited before, because I always respect copyright. I mean, I wouldn't know if you did that, but like, I would be remiss if like I, ever had you guys go to one of those sites. So anyway, if you get what I'm saying. All right. Yes, the 12th edition is where I'm going to have the problems coming from.
Is it okay if we read the chapters from the 12th edition as well?
Yeah. Like I haven't, so even though officially the 13th edition is the latest one, I only got the 13th edition 3 weeks ago. So I can't adjust my material for the new edition. I'm going to look through it and see if there's anything new and cool. But since I bet it's the same. I bet the problem numbers are different. So just stick with the 12th edition.
Thanks.
I would have no idea what that last thing is, Michael. So, I mean, I'm sure that's, you put that for people, don't go accidentally to those kinds of websites. Right? Absolutely. I'm glad you're letting other people know not to accidentally go to those things. Anyway, so yes, I fully expect you to always spend $100 on every textbook. Yes, exactly. Anyway, okay, so you calculate from the lunar and solar eclipses. So the lunar eclipse is when the shadow of the Earth blocks the moon. And it actually blocks the moon over a range of sizes, so it actually enters the shadow for a bit. But if you're going all the way around to the solar eclipse, the moon's shadow doesn't block a lot on the Earth. It tapers down. It doesn't actually reach to 1 point exactly, but it almost is like a single point. So we're going to approximate this. We can do more sophisticated math later, but to get a little rough estimate, it basically tapers down to 1 moon diameter. So basically this shrinks down, the shadow shrinks by 1 moon diameter to a point. So the Earth is also, assuming that we have circular orbit here, is also going to shrink by that same distance. And we found out the Earth's shadow at where the moon is 2.5 times wider than the moon. So that means that, let me shrink this down. This means that the Earth's diameter must be 3.5 times the moon's diameter. Here we go. Hold on one sec. Select all, copy, and paste. Okay, hold on. Let me shrink this down. There we go. Okay, let's delete this. Boop. Okay, make sure to bring it down some more. Okay, here we go. So, here's the diameter of the moon right here, and here is the diameter of the shadow of the Earth right here. So the diameter of the moon is going to shrink down to a single point down here, about. So, the diameter of the moon minus the diameter of the moon is basically 0 right here. Here's the diameter of the Earth right here. And here, since it shrank down by 1 diameter of the moon, it's going to be the diameter of the Earth's shadow, which is going to be about 2.5 times the diameter of the moon. Hold on one sec. Apparently didn't copy. Come on. I think I need to close some stuff. Not right now, though. Copy and paste this in. I'm updating old notes right now, and they'll be all posted onto Canvas. So, within 5% of the actual value, the accepted value now, the diameter of the Earth equals 2.5 plus 1 moon diameter, because we subtracted 1 off when it shrunk for the shadow, and we get about 3,640 kilometers. Kind of clever. You could do this. I mean, it'd be a little tricky to get, both eclipses, but you could do it. This is why I'm showing you this and going over this from the textbook, because it kind of is kind of clever on how you can make measurements. Any questions on this?
Yeah, can you go over one more time, like the whole equation, starting from the diameter of the moon minus diameter of the moon?
Oh, so right here, when we have the solar eclipse, the moon almost shrinks down to a single point. It doesn't exactly, and you'd have to have more sophisticated analysis if it didn't, but it's pretty close to being a single point. I'm doing an approximation. So we're saying that it shrinks down to a single point when you have this right here for the solar eclipse. It's not quite a point, but it's close to a point. We're going to make yes, Addie.
You weren't done with your point.
Okay, yeah. And then, I'll come back to you, yes. And then, so that means that the Earth is also going to shrink down by the same amount. So we're also making an approximation that, so we're making a couple of approximations here. We are making a couple of approximations here. One, that the moon's shadow tapers down to a point. to that the moon's orbit is circular. It's not perfectly circular. It's close to, but not exactly. And so therefore, the distance from here to here is the same distance as from here to here.
Right. Yeah.
Okay? And so, once we have these assumptions right here, that means that the Earth is going to shrink down by the same amount here that the moon's shadow did here. That's where this is like dm minus dm, diameter of the moon minus diameter of the moon, is about 0. And so the Earth shrinkage to the Earth shadow is going to be the diameter of the Earth minus that same diameter of the moon that we don't know yet. We found the diameter of the Earth from Eratosthenes. We need to find out this right here. We can measure this right here as 2.5 times, basically watching it and seeing it going through the shadow. So it's 2.5 times the diameter of the moon, which we don't know yet. So we can add this over to the other side to give you 2.5 plus 1 diameter of the moon equals the diameter of the Earth. Divide this over, get the diameter of the moon is 3,640 kilometers, roughly. Now, if you heard the term supermoon, what they're talking about is when the full moon lines up with the closest approach, which is why it looks like it's super big. Because the moon doesn't orbit exactly in a circle; it's in an ellipse. We'll talk about that later, though.
Thank you.
Brandon, do you have any other follow-up questions, or
Excuse me.
you have another follow-up question, or?
I mean, I'm guessing this is not the last time we'll like see about this stuff, right? Like,
No,
all
just
right.
to get you started.
All right, cool. Thank you.
And Addie?
Yeah, I had a question. I think I may have resolved it, but can I test the logic with you and you correct it?
Please, please.
So I was curious how we would, if we're trying, if we've found that the shadow of the moon is of the Earth is 2.5 times larger than the moon itself. I was wondering how we would gauge that, because the shadow is going to be larger than the surface, and we can't compare a shadow to the void of space. And so then what I came up with as a resolution for that, and I don't know if it's correct historically or as an approach, would be to measure the arc of the angle of the shadow and then see where that would complete its
I think that might work. That's not what they did, but I think that might work. What they did is they timed how long it took the moon to go around the Earth, which 1 month, about, and then figured out like how fast would it have to move through.
Oh.
They
Okay.
timed the speed, yeah.
Okay.
Yeah, it's actually, I am skipping over that step of how they actually measured this. Addie, that how they actually measured that this was 2.5. You're like, wait, how do you measure this? Because like you're not measuring against some background right here. You can also use some background stars as well. So it's not like the background is completely black. There's some, well, it's hard to tell in Los Angeles,
Right.
but there is some background stars as well that the moon is going to block. Even during the eclipse, that's also going to block those too.
Okay. Thank you.
Yeah. I'll have to look at exactly what Aristarchus did, because I know that's how they did modern stuff, but I'll double check on how Aristarchus did exactly, because I don't remember all the details behind what he did. But that's a really good question about how you measured this right here. But yeah, I'll welcome questions like that about like how to understand how you get these measurements, because that's, you know, the fun part of science is like, wait, how do they do that?
Right, because I've witnessed both lunar and full solar eclipses, and back then we didn't have all the context of contemporary astronomy. So how would I, as a layperson witnessing this, go about what we have now? So look into it further as well.
Yeah, no, and actually, it's actually about that time to take a break. Let me go ahead and take a quick little look, and I'll take a little peek, and I'll probably have that answer in a couple minutes. But before we take our break, any questions on this before we take our break? No. Track down the answer to Addie's question.
Thank you.
No problem. I'll fully admit when I don't know something. I don't know exactly what Aristarchus did, and it'll be a process that we all learn together. All right. Then I will see you guys in 10 minutes, and we'll be starting back up again at 3:20. All right. To answer Addie's question about how we could actually measure that 2.5, so you can do it in a couple different ways. Aristarchus of Samos did the way that I said, but Addie's works too, where you measure the curvature of the shadow on the moon. Here's an article that actually talks about both and a third method in detail. If you're an amateur astronomer, I mean, I teach astronomy sometimes, not at SMC because they're different departments from the physics one. But yeah, there's an article right there that really goes into detail about that. Here is more detail about Aristarchus of Samos on Wikipedia, and also in particular his writing on the sizes and distances, which is basically what this is, the textbook that I'm talking about right now, on the sizes and distances. But let me go ahead and so going back to here, what Aristarchus did is that he didn't know how far away this was yet. We're going to talk about that next. That'll be the next thing we're going to do. We didn't know this distance yet. We knew this size. We knew what DE was. We didn't know what this was yet. So what we did is we knew how big it was on the sky, about half a degree, and how long it took to go around. We approximated at the time that it was circular, and that was roughly correct. Not exactly, but gave you a rough estimate. And that kind of told you what this size was. That you time it and compare that to the period of the moon, and that gives you the size relative to the diameter of the moon. That's where this 2.5. I don't have time. I should actually go through that math. They actually do it myself, because that's how you really understand it, is when you do it yourself. I actually have not done that yet. But now, you all inspire me to go ahead and dive a little deeper. I'm going to dive into that paper that I just posted there. This one here, if you're kind of curious. This one here, the one I put in the chat. So we're going to talk a bit more about what these all mean, about whether penumbral versus umbral shadow. This is like incomplete shadow versus complete shadow. And you can basically time it. Whoops. And you can actually get some good timings off of it. So we got some details here, some math if you want to dive into it. This is basically how much of a degree does it move across the sky per hour. So yeah, it basically has a whole bunch of timings that you can basically, if you're curious, you want me to walk you through it, I'll happily go through it. By the way, it's not exactly 2.5, it's averaging 2.65, but it can be as small as 2.5.7, 8 to 2.735, depending on where it is with its elliptical orbit and how it lines up with that. All right. Thank you, everybody, for inspiring me to dig a little deeper. It's always fun for me to dig a little bit. All right. Any other questions about this? This is really interesting to me. About how so while Addie's is I think it was, they said that the method that Addie was proposing was not what Aristarchus did, but is what another Greek astronomer did. Who was it? I saw that name. Where'd it go? It was the one that Addie suggested was done by I lost the name. It's somewhere in here. Hipparchus. this guy here. By doing the curvature of the shadow on the moon, of the Earth's shadow on the moon. Okay. Any other questions? That was a really good question about where did this come from? Like, you just give this number. Where did it come from? I really like those questions. Sometimes I even learn. I often learn too. By the way, eclipses don't happen super often. They actually since the Earth and Sun are super far away, I'm stealing this from your textbook. I'm going to borrow a lot of stuff from your textbook and other places because while my drawing skills, like I'm using Adobe Illustrator here to try and get the best drawings I can, and I'm going to use my iPad to draw on it too, I sometimes just do better diagrams from them, so I'm going to steal them. So here is the moon's orbit here, drawn as a circle, even though it's ellipse, and here's the sun right here. The Earth itself is too small to see. So this lineup is rare, and eclipses are even rarer because the moon's orbit is tilted at a 15-degree angle to the plane of the Earth's orbit to the sun. So there's like an eclipse season that kind of happens. We'll talk more about that when we talk about orbits later, but yeah, it doesn't happen all the time. And by the way, by eclipse season, I don't mean it happens at a single monthly time each time. It changes. It doesn't line up exactly. But it only happens in certain periods where they all happen, like you could have the lineup happen or not happen. Cool. Other questions? So, let's go ahead and get the distance to the moon now. Now that we know the size of the moon, we can actually find out the distance of the moon now, how far away this is. Because before I didn't know what this distance was, we just knew that it tapered some. When the moon's this far away, it tapers this much. So, we're going to go ahead and talk about what the size of the distance from the Earth to the moon is now. What? I thought I copied this. Copy this now and paste it.
Sorry, I don't mean to monopolize your time with questions.
Sure, no problem.
So something that I was just reading under the FYI on this page that you're copying from, and I realized, so these, you're drawing from a retrospective of the accumulation of astronomy and physics when you're explaining this lecture, but the context of when Aristarchus or we'll skip the name. We're
Eratosthenes,
doing Eratosthenes. It was a geocentric model of our solar system. So,
well, it wasn't fully accepted yet. This was the time where, so Aristotle wasn't the consensus yet. It wasn't until the Catholic Church later did it become like a very rock solid kind of consensus. Aristarchus actually kind of was on the side of heliocentrism. So it wasn't like I think Eratosthenes was a geocentrist, if I remember correctly. I have to double check on that. Don't quote me on that. But Aristarchus actually leaned to heliocentrism. It was not settled debate. But probably if there's a rule, unless it's about art, and if it's Aristotle, he's probably wrong about it. That's kind of my rule of thumb.
Okay.
He was wrong about chemistry, physics, politics. Yeah. So, yeah. So it was the Aristotle very smart guy, wrong about a lot of things.
Oh, I didn't mention Aristotle. Aristarchus.
I know, yeah, but I'm saying the person who was the heliocentrist promoter and the one that basically everyone pointed to is like, oh, the guy who knows everything was Aristotle.
Oh, got it. Okay.
That's why when you brought up geocentrism, that's why I had to bring up Aristotle. Although I think, let's see, was it Hero of Alexandria? Because a lot of them, these were like people in Alexandria. I believe also was, I think he was a geocentrist too.
Because we also had the Ptolemaic model of the solar system, right?
Oh
was
yeah.
circles.
That's who think of Ptolemy. Yeah, Ptolemy
So
also
I'm-
believed it was that too.
So
So
I'm
Ptolemy,
curious.
Aristotle believed in the geocentric model. Yes.
Okay.
What are you about to say, Adi?
Well, I'm curious because the physics that we've derived from those models are consistent with a change of our understanding of the model.
Yeah. And so we change our models a lot in physics. So about whether that's gonna, it's actually being flexible and being willing to be wrong is part of being a scientist, and being willing to have things proved wrong. If you're curious about how we changed and how the evidence like accumulated from like Aristarchus kind of having a hunch that I think it's a heliocentric rather than geocentric, because Aristarchus didn't have like the mountain of evidence that kind of accumulated in the early Renaissance. When it came to the early Renaissance, with like with Copernicus and Kepler, it kind of became it's the only one that makes sense. Before like being a debate you could have, at least in the Western field. I don't know the traditions in other places, so I'd have to look into that.
Thank you.
You're welcome. Yeah, very good question. Other questions? I mean, this is fascinating to me too. About like historically, how did it all shake out? Who believed what when is like a very fascinating question, and it is an active area of research that we're constantly learning more and more about. If you're curious about what I was just talking about with Addie, there's actually a series that I highly recommend from I don't know if you've know of like the Green brothers, like Hank and John Green, the Crash Course people in SciShow. I'll be recommending quite a few of their videos here and there. Well, more Hank Green than John Green, but Hank Green's history of science series is very, very fascinating. Highly recommend it. Come on, work with me. All right. So Aristarchus wasn't quite done after measuring the Earth. Earth-Moon distance. Next he did... Let's see, hold on. Where does this fit in? Oh, I see. So we do this. Okay, we do it like this. Shrink this down a little bit. Okay, here we go. So, let's say you have a coin. Here's going to be my coin right here. It's my watch, but I'll use it as a coin. And you close one eye. So basically, here's your eye right here. It's a single point. And you basically, something off in the distance, you're blocking it off with this right here. If you know the size of the object, the coin or whatever you're using, and how far away you hold it, you can use similar triangles to figure out the same ratio of the moon diameter to the moon distance, because we know the moon diameter from previously. And actually surveyors use this all the time, because usually you can't get to something super far away, but you can use this kind of technique. If you know this size and this size here, you can figure out what this ratio is too, if you know one of these two here. Usually surveyors know this distance rather than this one, but you can do it for either. Yeah. So the coin blocks the moon at 110 coin diameters. Whatever diameter coin you have, at 110 coin diameters, it'll block the moon. And so that the radius of the Earth to the moon must be 110 diameters of the moon, because this ratio is the same. Actually, since I brought up the crash course one, let me go ahead and track it down right now. I'll be recommending lots of YouTube videos, but let's see. Crash course, history of science. Also, the crash course physics, well, it's more like computational one. If you want to watch it to kind of give it a different sense, if you want to go into that, I also recommend it too. She's a really good, has a really good one. But here is the crash course history of science. Because it's like interesting about what we choose to teach about science. And of course, it has to be a selection. You have to make choices. Like I'm even talking right now, I'm making choices on what should be I talk about and what I don't. So. Yeah. So I love philosophy too. All right. Any questions so far? All right. So Aristarchus wasn't quite done. He was going to go ahead and he gave measuring the distance to the sun a go. But there's a problem though. If you want to use the same method, one, it's dangerous. You could go blind because, like, you know, unlike the moonlight, which is not going to blind you, sunlight will, even during eclipses, because it turns out the solar corona. Corona here means crown, which is why it's used on beer, and also on that pesky virus that just will not end ever, because it's a crown. Right? It's crowns of, like, you know, spike proteins, or crown as in, like, you know, a halo around it, or, you know, whether you just want to think, oh, your beer is kind of royal. So, corona means crown. So the solar corona is actually hotter than the solar surface. So the light from that, while it's not quite as intense, it has same energy that can damage your eyes. So don't stare at the sun, because you can still go blind even during eclipses. So that's one of the problems. There's a couple others though. So you could go blind. We don't know the size of the sun yet. And for also annoying coincidence, well, it allows us to have eclipses, but the sun diameter, the sun distance is also 1 over 110. So you can't get anything new out of it by doing the same trick that we did with the this right here. So they, both the sun and the moon, taper at the same angle. About, well, not taper, occupy the same angle. Occupy. I'm going to clean up this a little bit. Occupy. Pi. The same angle in the sky. Okay. So we can get a little clever. Here's what Aristarchus tried. And it would work in principle. That's what's so cool, is that it also works. It just, he didn't get the right measurement. So everything else, he was getting really good measurements. This one, while it would work, he didn't get a good measurement for. Instead, he said, instead of having eclipses, do it at half moons. So you have the angle right here, and you have this as a right angle right here. He didn't have, like, you know, trig functions yet, but if you know this angle here, and you know this distance right here, the distance between the Earth and the Moon, you could find out this distance here. Because this would be, if you know this distance, and, hold on. This would be like the first or third quarter. Actually, hold on. Select all, copy. Let me just delete this, shrink it out. Yeah, sometimes when your Zoom goes in and out, yeah, let me know if it goes out for anyone else, but yeah. I got fairly good internet, but it does cut out sometimes. If it cuts out for you, just let me know. So here's the Earth-Sun radius here, and it's the cosine of that, by the way. And we knew that it's Earth-Moon radius. So Aristarchus measured 87 degrees, and it's really hard to measure this because this distance is so much bigger. This is not to scale. This distance is so much bigger than this right here that it, remember that picture I showed you a couple ones ago? You can't really even draw it. This is actually supposed to be 89.8 degrees. So rather than like 16 times further away, it's actually 400 times further away. Maybe he was like, got a bad measurement, thought that was okay. Or maybe he got like a better measurement and like, nah, it can't be that far away. It can't be that big. Because space is enormous. Sometimes the space distances in space, this is like this is called the cosmic ladder, by the way, where we basically take measurements that you can start with and you build on them. So space is enormous. Kind of inconceivably enormous. Yeah. And we're just talking about within the solar system. We're not even in the outer solar system or even leaving the solar system yet. I'll make little forays out to the solar system. Although this is a physics class, not an astronomy class, I won't be able to go into too much detail, but there are a couple of textbooks, if you're curious, I can recommend to you. If you're like Addie and have a passion for astronomy. Oh, of course, it is one of my passions too, so I will definitely allude to it. So, this is how you can measure this distance here. It's 400 times this right here, and that gives you, if you do that one, you get pretty close. Oh, your video got blurry? Oh, yeah. Is it getting blurry now? That might be on my end then.
Clarifying question?
Sure, go ahead.
The cosmic ladder, is that applicable to physics or astronomy?
That's astronomy in particular. Yeah, it's the cosmic ladder is like, using a measuring tool, like basically taking a ruler. Basically, once we get this distance right here, the radius between the sun and the earth, we use that as our measuring stick for everything else until we reach like a boundary. Then we have to have like, what's called the standard candle. And then we basically base off of all those. And a lot of astronomy is just calibrating that to get the distances right. So, bless you. Cool. All right, I'm glad it went back. Hopefully, it'll be recording in the best recording quality if you have to look back on the video. It usually gets posted the same day. It used to be much slower, but it looks like Zoom has gotten faster at posting the videos that it records. But yeah, that's the cosmic ladder. It's really in reference to physics, but like some cosmology, there's some like, we're actually working out whether, you may have heard something called the crisis in cosmology, where it's about, we think that one might resolve, which is called by calibrating things better. And that's what a lot of astronomers do, is they try and get better and better measurements. It's also true for physics too. There are certain people in physics where they just try and get things more accurate. Rather than getting new measurements, trying to get the same measurements better, and maybe you might see something new because it's a little unexpected. Maybe F doesn't exactly go MA. Maybe there's something else there. We're pretty sure it is. Unless you're, in modified Newtonian dynamics, which, is no evidence for right now. Right, yes. So this 400 comes from doing the cosine of 89.8 degrees. So if you do the cosine of 89.8 degrees, you get, assuming right mode, yes, cosine of 89.8 degrees, you get 0.0349, and you do 1 over that. Hold on, what? It's a ratio. It's a ratio. Now, so you could actually measure this in kilometers, but this is a ratio here. So it actually has no units because these are both distances here. You're welcome. Good question. Hold on. That's not it. I'm not getting that. Anyway. So yeah, this comes from the cosine of this right here. Any other questions? You guys have really good questions, by the way. So if you want that unit, though, call the base, the very bottom rung of the cosmic ladder that I was alluding to, it's called the astronomical unit because it's basically so ubiquitous in astronomy. Gotta shrink this down. I'm basically adapting this from a different version I had, where they were much bigger. So it's called, it varies a little bit, being 147 times 10 to the 8 kilometers in December to 1.52 times 10 to the 8 kilometers in June. You notice that you're actually closer in our winter than we are in our summer. Does anyone happen to know why? So what's going on? What causes the seasons? Does anyone happen to know the answer to that?
It's the tilt of the axis being further or closer away to the sun.
Well, it's not the distance though. You're right about the tilt of the axis, but being further or closer away isn't exactly right because you're actually closer in December.
Oh, it's the angle at which the light and the radiation is penetrating the atmosphere.
Mm-hmm. So it's like, consider like being head on, like this. Well, hold on. The light being like that, and hold on. So we have, let's say it was like this. We're close to this. And we're going to go ahead and, so like this. So this would be like, in June. It'd be near dead on. It wouldn't be exactly dead on unless you're in the tropics, but let's go ahead and do it in December. Or whatever, if you're in the southern hemisphere, if you're in their summer months. What happens is the angle, as Addie was saying, comes at a much steeper angle, like this. So you can see this area here is bigger than this right here. And so there's more solar radiation per square meter in the summer than in the winter. Also, the day is longer than summer, too. There's two effects. One is this intensity is larger, and two is the day is longer. So, let me see. This is the effect of the Earth's tilt for the seasons. Intensity 1. More solar energy is concentrated per square meter or square area. Concentrated per square area. Also, the day's longer in the summer. So it averages about 1.496 times 10 to the 8 kilometers. We got better measurements with the transits of Venus and the constant aberration, which is when the sun in the sky appears in slightly different locations based on the Earth's movement. Now we use radar reflected off of Venus and Mars to get even better. We're just silent. They don't make a sound, but you know. Because there's no sound in space. All right, so that's the actual distance to the sun right here. Marcelina. Any other questions? So to give you a sense of how accurate we've gotten pretty accurate. Let me go ahead and give this what the modern estimate is. Time. We're close to the end. So, the radius of the sun to the Earth average is about 1.459 bunch of digits times 10 to the third. And we've gotten accuracy out to here with this, like, you know, radar. The way it works is through the Doppler effect. You know, like, whoa, whoa. Like, you know, when a siren goes, like that. That kind of Doppler, except for light. And it's what we do. That's how they actually do it for storms. Actually, they can track the storms. We can also do it for other moving objects with light. We'll talk about that later. So how we get the size of the sun? We actually can't, we're going to use it, what's called a pinhole camera. And I remember once I had a student that said, like, I tried looking through this right here and like it hurt my eyes so much. And I was like, oh no, don't look through this pinhole camera. You project it here. No, it's a way of not looking directly at the sun. So what you do is you have the sun right here, you don't look at it. You still look at the ground right here, and here, through a pinhole point right here, you take a piece of paper, you punch a hole in it, and you get an image form down here. And you can actually change this distance to be in focus right here. By the way, that when it's in focus is when it's you get this ratio from here to be 110 as well. That's what your eyes are doing, is actually to adjust your size of your lens to focus on different things. You know, your eyes can be in focus on infinity or in that. We'll talk about that when we talk about vision later, but yeah. Your eyes also have a pinhole, your iris, that basically allows images to form on the back of your eye. So this is kind of what with minus the lens, this is kind of what, you know, a human eye kind of is. You got an opening and a place where you can get the image captured. So, you may have seen during eclipses that if you have little holes in the leaves, you actually can get this kind of like pinhole camera effect and get little images. Like this. In fact, who was it? Renoir also did like during a solar was it during a solar eclipse? No, it wasn't a solar eclipse, but he did have the pinhole cameras from the leaves in this Renoir painting, like this right here. All the pinhole cameras. See, like, these are images of the sun here in his painting. These are this just here. And you actually can get the size of the sun this way, because it's 1/110 again. So hopefully this kind of like, we're kind of almost out of time, but I'm going to talk a little bit more about the scientific method and how we go about things a little bit on Wednesday. But hopefully you guys had a pretty cool introduction to, a little bit of astronomy, but how we go about building off of older measurements and getting new ones. That's the main reason why I walk you through this, is you can see how we started with the size of the Earth, then we found out how big the moon was, then how far away the moon is, then how far away the sun is, and then how big the sun is, and then we could go out further. Once we have this distance, the astronomical unit, we actually can go much further. Not all the way, we have to do other things too, but we can get a lot with that. So it's just about how you can take old measurements and build new ones off of it. Do you guys have any questions though before I let y'all go?
I do. So we should start chapter reading by today tonight into chapter 3 by Wednesday, right?
Yeah, I'd recommend it. Or at the latest, have it done by Friday.
Okay, all right.
Yeah, basically, I basically finished up chapter 1 today, and we'll get through most of pretty much all of chapter 2 on Wednesday too.
Okay.
Any other questions?
And so will the exams be mostly from book information or information that you taught?
Yes.
Or both? Okay.
Yes. So it's important to both read and pay attention. I'll give you other resources that I'd like you guys to go to as well. Other questions? So I'll set up a Discord for you guys, so you guys can all start getting to know each other, and also post that assignment to introduce yourselves, and I'll make a little video myself introducing myself. That way you can all get to know each other a little bit.
That'll be on Canvas as an assignment.
Yes, you'll see it as an assignment on Canvas. You're welcome. Yeah. Sorry, sometimes private messages come in when they say thank you, and it says thank you, welcome. Yeah. So. Any other questions I can help you before I let you guys go? Oh, no. I actually prefer having you guys on camera. If you have your camera off, I would like what Grant did right there, where you have a photo or something on you. Like, I'd rather have something. I'd rather you see faces. I love seeing faces, but I understand not everyone can. It's, it is your guys' home. I don't mind you guys seeing my home, but if you guys, at least if you are gonna have your camera off, please have a photo there. I'd prefer it, because like it's hard to have just like a bunch of black squares. So but I love seeing your faces if you are willing. Any other questions? Oh, I almost forgot. So, that's a good question. Contacting me. I did skip that part. Let me go ahead and go over that right now. So I did allude to it, but I'll go ahead and show you how you do it. So, let me go ahead and share this on Canvas. So, You can, of course, email me, that email in the syllabus, or you can do Canvas messages right here in my inbox. That's if you want to have private messages with me. If you want to have like, homework questions, I highly recommend you use Pronto here. And that basically is going to be like a chat room for the whole class. You can do like messages and ats. Like unless you at me, I'm going to assume that you're talking to the whole class. So you can at me by doing, at Robert's there, and that's how you at me. That's how you'll know that you're addressing me. And there's also similar in Discord that I'm going to set up today. This is like this is not Twitter. It's okay if you at me. Okay. Any other questions? By the way, Discord and Pronto are going to be more your spaces. So unless you ask me to help, I will assume that you guys are working it out amongst yourselves. Other questions? By the way, Pronto, there's also an app for Pronto too, so you can also have it on your phone. I have it on my phone, but in terms of the turnaround, I'm going to promise that I'm going to get to it within one day if it's Monday through Friday. On the weekends, I might get to you sooner, but at the latest, it'll by Monday. I may not be available on the weekends, but on the weekdays, I'll have a pretty fast turnaround. Other questions? Well, you guys have me. Like, here's the tutoring center and the online calculators. So you don't need to, if you don't have a calculator, you don't need to buy one. You can just use this one here. Like, let's see. I want the cosine of 89.8. There it is. But you have to do degrees. Wait, hold on. Is it not doing it right? Is it doing radians here? I think that's radians. So hold on. You can convert it to degrees. We're going to do 2 pi divided by 360. And that's the right answer. It does in radians, so. But
is there going to be things on the exams that we're going to have to use decimals for?
If you do, I'll give you access for it. I think there's like a built-in calculator I can have for their exams, but yeah. Let me know if you don't have a calculator at home, like a scientific or graphing calculator. But mostly, since this is a conceptual class, most of the equations will be relatively straightforward. It's about using the right ones if there are some. Mostly it'll be mostly concepts than calculations. There's going to be some, but it's mostly going to be focused on concepts. Other questions? Oh, you guys were nice and lively today. I really enjoyed, lecturing you guys. And I will see you guys. You're welcome. I'll see you guys all on Wednesday then at 2 p.m. I'll also have office hours at 1 p.m. on Tuesday, 2 p.m. on Tuesday, if you would need to meet me. All right. Bye, everybody.
Thank you.